Okay, in this video we are going to do the same procedure as previous, finding an integrant factor to convert a non-exact differential equation into exact differential equation. So as you can see, this is the same procedure until this point. In the previous video we assumed that the function of two variables is only function of x, but now I'm going to do it is only function of y. So here I took the liberty to change the value, so now it is only function of y. So the procedure is very similar to the previous video. So let's continue here. So in this case, the partial derivative of w of y respect to x happens to be 0. Y is 0 because w of y is supposed to be only function of y, and you are taking the partial respect to x. Y is supposed to be a constant, so this is equal to 0. So what is left here is going to be, and here also, because it is only function of y and you are taking the partial derivative with respect to y, then this is no longer a partial derivative, it becomes a normal derivative. So you have w of y partial of m respect to y plus the m derivative of w of y respect to y, normal derivative, equal to w of y partial of m respect to x. Okay, now, and that is 0. Okay, so I'm going to move this to the other side and factorize the w of y. So what happens here is that the m derivative of w of y respect to y is equal to w of y times this partial of m respect to x minus the partial of m respect to y. Okay, now this is a variable separable differential equation. As you can see here, it's the same procedure as the previous, but now it is with y. Okay, so let's separate the variables. So what you are going to have here is the differential of wy divided by wy. I just pass this as a division, the differential of y to the other side, and the m as a division. So what you are going to get here is equal to the partial of n respect to x minus the partial of m respect to y over m differential of y. So you can see here is variable separable because here on this side you only have w of y, and here you have only function of y. So, but here you will have the same restriction. But let's talk about that later. So you are going to take the integrals on both sides. So the integral of this is the natural logarithm of w of y, and that is equal to this integral. We leave it as it is, integral of the partial of n respect to x minus the partial of m respect to y over m differential of y. So let's take the exponential on both sides. So what you are going to get here is w of y is equal to the exponential of the integral of the partial of n respect to x minus the partial of n respect to y over m differential of y. So here you get the same formula, very similar to the previous one, but here the difference here is that it's expected that this to be only function of y. So that means that this formula works only if this is function of only y. If this doesn't happen to be only function of y, then you cannot use this formula, and you will try the other formula. Alright? Y should be only function of y because that is the assumption we did here, only function of y. So it is expected that this is only function of y. Okay, so with this other formula, you can try to make this non-exact differential equation into exact differential equation. Now, which formula to use, the w of x or the w of y? Well, nobody knows, so you have to try both. And the one that is only function of one variable, then you have to use that. That formula. Now, it is highly possible that you have an a non-exact differential equation, and you try both formulas, and neither of them works. So that means that that differential equation is not an exact differential equation, and you have to use another method. By the way, I forgot here, On this integral you are supposed to add a constant, alright? Well, that assume that constant to be 0, here and in the other formula. The constant there, it doesn't change the things, alright? So now you have the formulas to try to make it, try to force it to make it exact differential equation. On the next video, let's use, let's see an example of using these formulas, alright? See you in the next video.